Hello everyone, welcome to the Arbitrum Workshop. Let's see if yeah. This will be the first module out of 4 modules. This module is called, as you can see, Arbitrum's role in the Ethereum roadmap. So this one will be a bit more theoretical, where we will be going through like the blockchain history and how we came to where we are today and how Arbitrum fits into this. And then we will get, in the next 3 modules, we will get our hands more dirty and get to actually coding together. So about me, my name is Jack. I usually go by the username crxjsi.eth online. I am a Solidity and Rust developer, and I've been working this space, the Web3 space, for the past 3 years full-time, mainly within the niches of trading systems, cross-chain intent, and trusted execution environments, the latter of which I'm currently very interested in and trying to find more time to research. And when I'm not working, I'm a bit of a hackathon addict as well. I am at like 20 plus hackathons at this point and counting. So we have prepared a GitHub repository. So please feel free to scan this QR code because we will have all of the contents here that you will need. Also, we have these presentations in written form there in a blog that me and Alex have prepared for this presentation. Aside from that, we also have a Telegram channel where you can request some testnet funds that you will need later. I will show this QR code more times, but so we have the Telegram channel here where you can request testnet funds for superposition. So let's go ahead and get into the content. So blockchain history, of course, we will start with step 1 being Bitcoin. So I'm pretty sure most of you are familiar with Bitcoin here, but I'm just going to go through it briefly so that we're all on the same context. So in 2009, an anonymous programmer / cypherpunk under the pseudonym Satoshi Nakamoto released a white paper that was called Bitcoin, a peer-to-peer electronic cash system, where he described and later came to implement a decentralized transaction ledger, which allowed anyone to send money to anyone else in the completely independent of banks and central actors. And this was made possible through some clever usage of cryptography and something called proof of work, which is basically a consensus mechanism where multiple peers can verify information to be true without having to manually interact with each other. It's all happening autonomously. This consensus mechanism is put to verify the integrity of transactions that go to the Bitcoin ledger and also to record the transaction onto the ledger. And Bitcoin was just that, like a ledger, like accounting, bookkeeping. So you just have transactions. Alice sends money to Bob, Bob sends money to someone else, so on and so forth. So it was very minimal, but it was a big value proposition for its time because, like 2009, we were going through a financial crisis. People were starting to question banks and central actors. So having a system where you, instead of having to trust a central actor, you can just understand the system, and therefore you can verify that you own your money and you can send money to somewhere else, was a big value proposition. But people were thinking like, what if we could take this to the next step? How could we take this to the next step? And one of these people that asked these questions was Vitalik Buterin, who kind of asked like, what if instead of verifying transactions, we verify computations? And this question led to the development of Ethereum, whereas Bitcoin is like a decentralized transaction ledger. Ethereum's goal was to be a decentralized world computer with a shared state. So they did this by implementing a virtual machine called the EVM, which is powered by an instruction set architecture, like the actual thing that powers a real CPU, a computer, but all made virtually on-chain. So instead of transactions containing like transaction information, they contain opcodes that will execute on this virtual machine. So what this in practice means is that the blockchain is now programmable. So it launched with a programming language called Solidity that compiles down to these opcodes. So this gave everyone the option to create apps using the same transparency and verifiability. So following the launch of this, developers were having a few years where they did some very nice innovation, created decentralized alternatives to centralized financial systems. So like lending protocols, stable coins, and exchanges, so on and so forth. Terms such as DeFi were coined during this time as well. And while it was certainly a step up from Bitcoin, it was still leaving some things to be desired, such as, for example, gas fees. For every transaction that you send, you have to pay Ether in gas to execute these computations. And it was proved first time during 2021, when we had the first big influx of users on top of Ethereum, that these gas fees can get very expensive. So an Ethereum block can only contain so many transactions, and once you have more requests than what one transaction can actually fill, it's kind of pay to play. They implement this like fee market. So the one that pays the most will be the one included in the next block. This can get very, very expensive, like hundreds of dollars expensive. And also the block time is kind of long on Ethereum. It's 12 seconds. So even if you're under the assumption that you will be included with your transaction in the first block, you might have to wait up until 12 seconds, which is like, given how fast we are expecting our tech to go these days, no one has time to wait for 12 seconds. Aside from this also, Solidity is a great programming language, but it is very domain specific to just Ethereum. You can only create smart contracts on Ethereum or on an EVM compatible chain with it. You will not create like a backend with it. You will not create a desktop app or anything like that. You will always need more languages if you want to create the whole app experience yourself. And also, it's very, like, you need a lot of domain-specific knowledge to create a smart contract using Ethereum. So it's not always like very obvious to translate in and out of, you know, regular programming or programming on top of the EVM. So a lot of companies tried to implement different solutions to address these three problems. So we have companies that kind of completely scraped what Ethereum did and tried to implement an execution environment from scratch. So you get your Solanas or your Suis or your Cosmos compatible blockchains. And some companies thought that, hey, the EVM is nice, so we can just like expand on what we have and try to make it better. And people were starting to do roll-ups on top of Ethereum, which are EVM-compatible chains that derive some of the security from Ethereum, but they trade away some of their native security in order to get higher speed. So one of these roll-ups is Arbitrum, which I'm here to talk about the rest of the day. On this slide specifically, when I'm talking about Arbitrum, I'm talking about Arbitrum 1. So what is Arbitrum 1? It's a EVM-compatible optimistic roll-up on top of Ethereum. So EVM-compatible means that it's basically everything that EVM can do, everything that Ethereum can do, Arbitrum 1 can do. So if you create a smart contract that you can deploy on Ethereum, you can deploy that on Arbitrum 1 with little to no modification, and vice versa. Then rollup I just went through, it is scaling Ethereum. Optimistic is the most like interesting word out of these words, which means that that's the way that it's scaling Ethereum. So in order to understand what an optimistic rollup is, we need to understand how Ethereum is doing validation. So in regular Ethereum, like in regular mainnet Ethereum, it works in a way so that, oh, yeah, I can just keep going because it's just the same slide. It works in a way so that every validator that is verifying the network is running every transaction. So this is very, very secure. So if you have, like, for example, say 1,000 validators, every transaction will be run 1,000 times, and you can kind of see like what the result of all of these validators are, and you can easily kind of see what the consensus is of this and just ignore any diverging results here. Which is, again, great for security, less good for scaling, because if you overnight get twice the amount of validators, 2,000 validators in this example, you won't get twice the throughput. It won't be twice as fast. It will just mean that is 2,000 validators running your transaction, so you will have more security. So in an optimistic rollup, you kind of think that the blockchain is already so secure, so why not trade some of that away for speed? So generally speaking, in optimistic rollups, you have instead a system where every validator needs to stake money when they are validating. It needs to be a standardized amount of money. You can think about it as like a physical like vault that they are locking in their money, and it is locked. It remains locked for as long as they are validating, and it's already agreed upon a time window where, like, from the point where they stop validating, how long it takes for them to actually be able to reach their money. It can be a week, it can be a month. Doesn't really matter. So during this time, they stake this money as a form of like a testament to, I will be truthful in this system. So then when they are validating, the validator that actually records this transaction will be the only validator that is running this transaction. The transaction will be run elsewhere than the blockchain, and then only the result will be posted to the blockchain. And then because of the name, everyone remains optimistic that this person is truthful. If, however, someone thinks that this validator lied in some way, you have this vault lives as a smart contract on top of main Ethereum, and this vault also have a mechanism where you can challenge the results that they posted. So if you think that they are lying with their transaction, it might cost you like $1,000 to prove them wrong, but you will get the $10,000 bounty because of that. So therefore, it's in every validator's best interest to remain truthful. So here's more specifically, this was like broadly speaking how optimistic rollups do it. Here's how Arbitrum works from the point where you send your transaction to the point a block actually is created. So transactions flow in here from users to the sequencer. The sequencer is interesting. It's a centralized piece of code that is hosted by Offchain Labs, the guys that created Arbitrum. They are currently working on actually rolling this out to be a decentralized alternative, but for now it's centralized. Once the transaction hits the sequencer, it will be outputted in what's called a sequencer feed, and this will be a soft guarantee that your transaction is valid and will be a part of the Arbitrum blockchain. So from the user point of view, you get more or less instant feedback when you send your transaction, which is great UX. Then we can see that we have the sequenced transactions here. Also, the sequencer is in charge of one thing here, which is ordering the transactions, sequencing the transactions. So like in a first come, first served type of way. So we have the sequence transactions here, and then a validator hits what's called the state transition function, where they will take the results of all computations and they will update the blockchain everywhere where it's needed on every necessary smart contract, and therefore produce a layer 2 block. At the same time that they're doing that, they're taking this sequence of transactions, they're batching them together and compressing that, and they're sending the hash to this smart contract that I talked about earlier, that is the vault, and also where you can challenge the validators. So this smart contract on main at Ethereum will be like kind of where it all settles. So this is how Arbitrum is scaling Ethereum, and while scaling Ethereum is cool, Arbitrum also thought that they would address more of the problems that I mentioned earlier. So 2 years ago, Arbitrum announced something called Stylus, which is a dual virtual machine. So on one hand, you have the EVM. On the other side, you have the WebAssembly virtual machine. So I will be going deeper into what this means and how this works in 2 modules ahead of this. But for now, let's just say that this means that you can support way more languages, because WebAssembly is a very popular virtual machine. So all of a sudden you have support for Rust, you have support for Go, you have support for C, C++, SIG, C#, and so on. So onboarding for new developers is easier because these are very big languages in comparison to Solidity. Aside from this, Arbitrum has another product which is called Orbit Chains. These are like app-specific chains that anyone can spin up that will specifically help them build their applications. So the way that when I showed this sequencer here, you can think about this picture here, but instead of having Ethereum mainnet as the layer 1 chain that everything is settling down to, an Orbit chain is settling down to Arbitrum 1 instead. So it's a layer 3 chain. So why would you want this? Partly, this gives the option to have like hackable chains. You can like change things about the core chain that you want to specifically for your app. This can be things as changing the encryption algorithm. This can be things such as implementing maybe order book that is part of the core blockchain. You can go wild with ideas here. This also allows for horizontal scaling because since you only have your app on this specific chain, or might only have your app on this specific chain, you only have to take into consideration the gas fees that your own users are producing. So you don't have to be scared of someone launching this big NFT collection or something like that on Arbitrum 1, because that will spike the gas fees, which is pretty nice. So examples of people that are building on top of Arbitrum is, for example, Alex, whom I co-created this presentation with, is the founder of Fluidity, which are building the superposition blockchain, which is hosting the stylus app 9 Lives, which is a prediction market. I recommend anyone to go to that GitHub repository and check out 9 Lives. It's really amazing, that code base. Also, Robinhood, the big stock exchange, they are currently expanding to Europe, and the backend for their European branch is actually an entire Arbitrum Orbit chain. Lastly, last year I was in Argentina and Brazil, and they have this like local payment solution there, which is through QR codes. You pay in stores with QR codes. This is supported like everywhere in both Brazil and Argentina. And they have this startup called Peanut Protocol, which allows you to, instead of paying from your bank account with these QR codes, you can pay straight from your crypto wallet. And all of this settles down to Ethereum. So this is probably like one of the more like easy onboarding scenarios that I've seen out in the wild for crypto. So that will be it for the first workshop. I'm happy to take any questions. Otherwise, I'll see you in 10 minutes for going through the second module of this workshop, where we will be starting to coding. Now we're starting the second module, which is called Your First Smart Contract on Arbitrum. So now we're going to get started with programming a Solidity smart contract. Again, this is the link for our GitHub repository, so you find all the necessary links there for things that we will go over throughout this presentation. Also, you will find this presentation in written form in a blog post that me and Alex prepared before all of this. And again, this was the one that I kind of left open on the screen. So this is the Telegram channel that you can go to get superposition testnet tokens. So let's get our hands dirty. First thing I will need and everyone to do is to go to metamask.io if you don't have MetaMask installed, and install MetaMask. Next up, this second line here is not valid because the faucet for superposition is currently down. So instead of going there, you have to post your wallet address in the Telegram chat that I showed you. If I can change now to the to my computer, perfect. After this, we'll need to add the superposition testnet to our MetaMask. So we do this by going to chainlist.org, this domain here. Can you see, by the way, the text, or is it too small? Should I zoom in? I can zoom in for. Yeah, okay. Chainlist.org. And on this page, we need to connect our MetaMask and we need to press this check mark for include the testnets. Then we are searching here in the search bar for superposition, like this. You will see superposition testnet here to the right. So press this button, add to MetaMask. For me, since I have superposition in my MetaMask, I can zoom in case you don't see. Since I have superposition in my MetaMask, nothing will happen when I press this button, but for you will get prompted by MetaMask. So let me know when you've done this step, and I can move forward. Here we will add the superposition testnet to our MetaMask. So we will hit this check mark here for including testnets, and then we will type in superposition, and then we will add that to our MetaMask. When we press this button, add to MetaMask, we will get a MetaMask prompt. So next up, we're going to go to remix.ethereum.org. This is a text editor for Solidity code. So we will be going to, just the domain remix.ethereum.org. And on Remix, we will creating a new workspace, and I will choose blank here, and I will press finish. So we will create a smart contract that will store our favorite number. So we can all try to think of our favorite number right now in preparation. To do this in our blank project, we can just hit this create button to create a new file, and I will call this ETHCluj.sol. So every Solidity file is suffixed by .sol. That is how it knows that it's a Solidity file. So in order to create our smart contract, we need to write out some boilerplate code. So let's start here on the first line with writing PRA. And you can see here in the dropdown that we have pragma. So if we hit enter on that, it will spit out these two lines. So the first line here is referencing the SPDX license identifier is referencing to the license of this contract that we're about to write. And for this demonstration purposes, we can just keep it as MIT. Next up, we can choose our Solidity compiler version. So since every smart contract is deployed into the same virtual machine, into the same environment, it's up to every smart contract to keep track of what compiler they're using, because you have one thing that's kind of changing over time, which is like the latest compiler version, but they are still deployed on the same network. So in order to keep track of this, we are manually writing what compiler version it is. So for this tutorial, let's keep it to the latest and greatest, which is 0.8.34, like that. So in order to actually create our smart contract for our favorite number, it's quite similar syntax to these like very, very object-oriented programming languages. If any one of you have written any Java code, it's similar to how you define classes there, but instead of using the word class, you use the word contract. Solidity is very object-oriented. Then we call it ETHCluj, and we open up curly brackets. So within these curly brackets here is where we will be spending most of our time as smart contract developers. Here we will define like every global variable and every function that does the logic that we need to perform. So in order to create our favorite number, we will create a variable, a global variable. Solidity is a statically typed language. This means that every variable needs like an annotation to say what type this variable is. So we need to let the compiler know in advance, is this a number, is this a word, is this a Boolean? So we have two types for numbers, which is signed and unsigned integers. Signed integers are integers that can be both negative and positive, and unsigned are just positive. So the most default number type in Solidity is an unsigned integer of 256 bits. And we will do it public because we want everyone to know our favorite number, and then we can choose the name for our variable, which I will choose favorite number, like this. Then we can see here up in the left corner here, we have a compile button. We can press that, and we see here on the Solidity compiler that we have a green check mark. This means good. Our smart contract compiled. So this is like already a working smart contract, but it's not a very fun one because right now we're not setting our favorite number. It's just the default value, which is 0. So in order to choose what our number is, it's equals, and then we can choose our favorite number. I will write 8 here. I will press compile again, and then we can navigate here in the buttons to the left here down to deploy and run transactions. We can hit this deploy button, and then we get our contract down here. So we can open it up and we can scroll through the functions. This is the favorite number, so I will take that and I will call that. This will return 8, so it returns my favorite number. Very good. Also here with the green check mark, if I can just demonstrate how it looks in case I'm not writing valid Solidity, I can remove this 8 after the equal sign, and if I try to press the compile button again, I will get a red error. If I hover above it, it will say parse error, expected primary expression. This means that I have to say something after the equal sign. Otherwise, Solidity won't compile. So say that I want to be able to, throughout the lifetime of this contract, update what my new favorite number is. Then I need to change the state being our storage here with the global variable. In order to do this, I will write a function. So we use the keyword function. Then we can choose the name of our function. I will call mine update favorite number. Then within parentheses, we are sending in function arguments, things that we use to modify. So we will send in our favorite number, which again is an unsigned integer of 256 bytes. And we call it new favorite number external. So 2 things here. Number 1, for function arguments, you will see a lot of Solidity developers will prefix their function argument names with underscores. I find it a bit easier to read. It's not something you have to do, but I prefer doing it that way. I find it easier to read, because when you have these larger functions, you can kind of easily skim through every variable, and therefore you can kind of see if the variable comes from the function signature or if it comes from somewhere else. External here is referring to the visibility of this function. So in Solidity, you have 4 levels of visibility. You have external, you have public, you have internal, and you have private. So what does all of this mean? External means that function is only callable from outside of this contract. Public means that function is callable from everywhere. And internal means that function is callable from inside of this contract, and any contract that inherits this contract. Private means that function is only callable from inside of this contract. So which visibilities should you choose? Not everyone will agree on this. Personally, I like to keep it as strict as possible. So if the function is something that's like user-facing, that the user will interact with, I prefer external. And if the function is something that will only be used by other functions, like core logic that is not user-facing, I prefer private. And I switch it to either like a higher visibility only in the case that I actually need it throughout the development of my smart contract. So switch from private to internal or from external to public. Anyway, so to create this function, we will write favorite number equals new favorite number. So we send in what we send in from this function argument as the new favorite number. We compile, and then we are resetting here. Then we will try to deploy again. And now we will see in the functions here that we have 2 functions. So we can call favorite number again and get 8. Then we can go to update favorite number and send in something else like 10, transact, and then I can go back to favorite number, call it again, and you see that now it returns 10 instead of 8. So not all functions need to change the storage. We can also do what's called a read function, which is something that takes data from, like only returns data without actually changing anything. We have two types of read functions in Solidity. We have view and we have pure. So the difference between these two is that view is a read function that can read from storage. And a pure function is a read function that can't read from storage. So if we want to create a function which takes whatever our current favorite number is and multiply that by 2, we can write function and times 2. And it won't take any arguments, but it will be, again, an external function. Since we need to read the storage to get our current favorite number, it needs to be a view function. And then it will have a return value. The syntax for returning is similar to the syntax for sending in function arguments. So again, you say that you want back a uint256, and it will be called res for response. I open this up. Res equals to favorite number times 2, like that. I can hit the compile button again. We see that it compiles. I could have written this like this instead. Return favorite number times 2. This is also completely valid Solidity code, but I find it a bit more easy to read with this named return values. And also, especially with smart contracts, it's important to remember that you will spend usually more time reading the contract than actually writing the contract. So readability is a big thing in smart contract development. We hit compile again, we reset, we deploy the new one, and if we look up this times 2, we can call that and we can see that it returns 8, which is double of, or 16, which is double of 8. Yes?
Yeah, 2 questions. What does the with gas, the number and the gas,
it is trying to measure the amount of gas, and it is a bit buggy on Remix. This infinite gas is not true. It's not something you have to worry about, but it is trying to like estimate what gas it would be for these functions. If I try to change the here, so if I try again to say favorite number equals 10, for example, you will see here that I get an error right away. So function cannot be declared as view because this expression potentially modifies the state. So if I try to hit the compile button here, I will get an error. So yeah, we have that safety in place there. Good questions. So next up, we can also, from functions in Solidity, we can call other functions. So what if we want to take the result, whatever times 2 is returning, and we want to send that as a function argument to update favorite number? We can do that. So let's write function. I want to call it chain because we're chaining transactions together. External. Since we will be updating the state here, it can't be a read function, so therefore it just returns a value because I want to return what the new favorite number is. Like this, res. So we write update favorite number, and then within parentheses we write times 2, like this. And now we see here that we have a problem. We see that we have these red underscores here. We have a compile error. If I try to hit compile, we will get the error up here. If I hover above, we see undeclared identifier. Update favorite number is not visible at this point, which is pretty weird because if I hover above it, you can see here that it pattern matches with the favorite number that I have here. Same with times 2. So why is this? Remember what I said about visibility, that external functions are only visible from outside of the contract. This means that we have to change the visibility of these functions. So instead of having them external, we now have to switch them to public. Same here, we're switching this to public. Like that. Now it will give us a warning because we are not returning any results. So let's do that as well. Res equals to favorite number. Then we are compiling this again. We reset previous chain. Then we are deploying. And now let's expand the terminal a bit here. If I press this chain here, I can transact to it. And we can see here in the logs, we can expand them with this arrow down here. We see that it returns 16. If I press again, we can see that it will now return 32. So it will keep going like this. It will just double whatever our favorite number was, so 64, so on. So this is coming along nicely, but we have another problem with this, which is that this contract can only support one person's favorite number. If we were to deploy this on a network and have our favorite number, someone else could just update that. And maybe we want to keep track of everyone's favorite number, our friends too. We can do this. I can just remove this to function here. In Solidity, we have something called a mapping, which is a variable that takes an argument that acts as a key, and this key will point to a specific value. So, for example, the key could be someone's name, the name Jack, and that key could point to whatever my favorite number is. So the syntax for doing this, let's replace our favorite number here with mapping. Then we open up parentheses, and then the type for a word in most languages are string, and this is the same in Solidity. So string name, and this is pointing to a number, U in256, favorite number, and this will be public, like so. And I will name it favorite number off, like this. Personally, I find it very satisfying to name mappings, because when you name them like this, favorite number off, the syntax actually try to get data from a mapping. Looks like this: favorite number off. So if I were to try to get my favorite number, I would have these square brackets and I would send in my name here. So favorite number of Jack, it reads like a sentence, which I find very satisfying. However, to use our name as an identifier on the blockchain is usually not recommended, because, for example, me personally, I know that Jack is quite a common name internationally, so there are a lot of people with the same name. So therefore, if they update with their name Jack, they will just update my favorite number to their favorite number, meaning that, again, we will have the same problem, that we will overwrite each other's name. So we need something that's more unique to me. And luckily, we have that very easily accessible on the blockchain. We have, now when we created our wallets in MetaMask, what that creates is a private key, that from that we derive a public key, and from that we derive an address. So the address is our public identifier on the blockchain. So when someone sends money to me on a blockchain, they will send money to my address. They won't send money to the name Jack. And we have a type for this, which is address wallet. So let's change string name to address wallet here. Then in our function, we update this to actually take. So we write, instead of favorite number, we say favorite number off. So how do we reach the wallet? Do we have to send that as an argument to this function? Answer is luckily no. Whenever you are transacting to a function in Solidity or on the EVM, an object is created that's called message, and we write it like MSG, and then we can write dot. So message contains some fields. It contains data, it contains gas, it contains sender, signature, and value. And message.sender, that's actually the address of whoever is calling this function right now. So I hit enter on sender, then I try to compile again. Again, let's reset this and deploy latest version. I go to update my favorite number. Then I set it as 8. I transact. We see that it went through. Then here, underneath account 1 here, you can see that I have my public address, which I can just copy. And then we can go to functions again and take favorite number off, pass in this address here. We can see ETHCluj, which is ETHCluj, it matches. So I call that, and we can get that my favorite number is 8. Very good. Say, however, that we want to have more information that this is pointing to than just like my favorite number. We want the name again. We can do this by creating what's called a structure in Solidity. So keyword is struct. So what is a struct? A struct is basically like JSON, or like a collection of other data types. So you can build the data types out of a collection of other data types, like a form or a JSON object. So this one will take string name, and it will take uint256 favorite number, like this. So instead of having my wallet pointing to just a uint, it will now point to type info with the name info, like this. So in order to now update this structure, we need to send in my name to this function. So string, and Solidity is very particular about memory. So therefore we have with strings, since you can't really know in advance how long a string is, how large that data type is, you have to send what type of memory it is. You have 3 types. You have memory, you have call data, and you have storage. And all of these are used for different purposes. But 99% of the time you will want to use memory, like so. We name it name, like this, and then favorite number of msg.sender equals to a new instance of info, which takes name and new favorite number, like this. I compile, I reset this, I deploy next version, I press update favorite number. Now I send in my name as well as my favorite number. So Jack 8. I transact. Then we go back to the favorite number off, copying my wallet here, sending in the wallet address here. I call that. And now we can see that it returns Jack and the favorite number 8. So next up, when we are writing smart contracts, we have to think about that at some point someone will need to write a front end for our app, because most likely our users will not want to go to remix.ethereum.org to interact with our app. They want a nice front end, and therefore we need to keep track of like making sure that the front end is easy, the smart contract is easy to interact with from the front end. So in order to do this, we will create an event, because right now it's kind of hard for a smart contract. If you want to create something like a feed that will update every time that someone updates their favorite number, right now it will be kind of hard to know when to fetch new data from the blockchain. Like, do I query every possible address, or do I try to make something that only is triggered from when someone is updating their favorite number? What if I do that and their transaction won't go through? Will that endlessly be polling? So in Solidity we have these customizable alerts or events, which is exactly for that. Then the smart contract will just like say like, hey, this happened, and you can program what this in this context is. So favorite number updated, and it will return address, wallet, and it will return whatever that person's favorite number is. So in the end of the function here, we write emit favorite number. I will write favorite number updated. Favorite number updated, like this, and it will pass msg.sender, and it will pass new favorite number. So we can compile this again. We reset the state here. Then we deploy latest version. And now we will read again here from the terminal. So if I take update favorite number, I send in Jack and favorite number 8, transact. We can now see here in the logs that we have here an event favorite number updated, and that has our address as well as the new favorite number. Very good. So last thing I want to cover, I'm a bit over time here, so I will keep it a bit fast, is remember that by the start of this, we have a default favorite number. We deployed it with our favorite number. In case we want to do this again, like something similar to this, we can do something that's called a constructor. And a constructor basically is a function that will only be run once. It will only be run when you are actually creating the smart contract. It can never be run again. And it works similar to a function. So you write constructor like this. It won't have a name because, again, it will only run once. It will take some function arguments. This will be string memory name, and it will be uint256 new favorite number. And in my constructor, I will make it update favorite number and send in these function arguments here. I will compile again. I reset here. And when I deploy now, we can see that, I have errors. Why is this? This is because now, in order to be able to deploy, I actually have to give it these arguments straight up. So I have to give it right away up front. So I will have to send my name and my favorite number 8. I press update, and now you saw that it's deployed again with the favorite number updated. So now, because we've been deploying all of this on the Remix virtual machine, this is an EVM that runs locally in our browser. It's not live anywhere. If we would like to deploy it to a test network, for this it's important that you have the testnet funds in your MetaMask if you want to follow. We can change here to Remix VM to browser extension, and we can change select to MetaMask like this. Now it's important that we go to our MetaMask and we make sure here that we are connected to the custom network superposition testnet here, like so. After this, I will take this contract and I will trigger the deploy button again. That will open up MetaMask and I can confirm the transaction. So now fingers crossed that the transaction will go through, and there we go. I can copy this address. I can open another window here. I can go on Google and type superposition testnet explorer. Then I can go to the first one here, head to the home page, and I can search for the address that I just copied. So we see here that this is the smart contract that I just deployed. It has one transaction. It was triggered 33 seconds ago. So this is a live Solidity smart contract on superposition testnet. Thank you so much. So inside of this GitHub repository that we prepared, we have one folder that is called Stylus Challenges. This is like very much the same layout as the Solidity Challenges. So we have one that's Stylus Challenges and one that's Stylus Challenges Solved. And when you go in here, you can see that we have 3 Stylus Challenges. So if you go into like the full path into the project, so you have ETHCluj Stylus Challenges 1 Vault. You can take the URL here and copy this. And then again, head to the wizard here. And we can go to import from GitHub. And we can copy in here the link here to that challenge. We can import that. Let's see, no space left on device, OS error. I guess that's okay for now because I have already imported that version here. So let's try if you can. You get the same error. Then I will, because Also, the wizard, great tool made by Tolga. So we have him in the chat as well for that workshop, the Telegram chat that I invited you all to. So let's just see if it's something that we can work on. Okay, so it works now. So instead actually of doing the whole import from GitHub thing, you can instead head straight to the ETHCluj here, the ETHCluj tab in the wizard, and you have Vault, email, and lending. These are kind of in all different tiers of complexity. So I recommend you start with this template here, the Vault template, and it will be the same way as it was with the Solidity challenges. You will get here the full project, and you will have some comments with some challenges for you to solve. Also, in the chat, in this chat that we made together with Alex, where you send your addresses to get testnet funds, you can also ask questions there if I'm busy answering someone else. If more people at one time have questions, Alex will be able to answer as well. And it's the same layout as with the Solidity challenges. So for Stylus, we have the challenges here, and we have the challenges in a solved version as well. In between, every time that you run this, when you're trying to what's it called, like solve these challenges, you can write test here and run this, and that will be running the Rust tests for this challenges. The first compilation is always a bit slow, as you can see now, but they will run, and then the next compilation after that will be smoother. So yeah, start off with number one, Vault, and see how far you can come here in solving this. Okay, so Alex just wrote as well in the chat that you should look out for this to-dos here. So when you find something that looks like to-do, exclamation mark, that is what you need to implement. If you're watching this, I see that some people, when they are trying to create a new, use the template here, Vault, you can see that they get repositories private, so it's trying to import again from the GitHub instead of actually getting it down. So this is no matter if I'm trying to import it from GitHub here, or if I'm trying to use the template here. Okay, so when I tried to connect to my phone's hotspot, then it worked to create a new project. So try that to disconnect from this shared Wi-Fi and try to connect from your phone hotspot instead. So unfortunately, a lot of the time from this kind of challenge time went to technical difficulties, but we still have some time, and then it will be a break, and then we will moving on with the next module. But hopefully you will be able to read through the Stylus contracts, and you can also like do this whenever you feel like, if you want to pick it up later. We have actually all of the contents for these workshops on the blog, as I mentioned before. So we have all of these modules in written form as well. So you want to go to the Vault, and for me to give a brief rundown here. Yeah. So first of all, we're setting up Solidity interfaces. So these are to interact with Solidity style code. So these are from the ERC20 standard. So every ERC20 token will always have the balance of, the transfer, and the transfer from. So having the interface like this allows us to interact with both Stylus contracts as well as Solidity contracts. So this is just as an interface to use later on to actually interact with the ERC20 contract. Then we have the entry point here. This is the storage creation of the smart contract. So these are the global variables that's held in a struct. So our contract is called Token Vault. It has the token, which is an address, and it has total shares, which is a uint256, And we have shares off, which is like the mapping in Solidity, but in Rust instead. So we have a storage map, which takes in an address that is pointing towards a number. So query like how much, what's the balance of this address. Next up, we are preparing a lot of events that we will be using later on. Here we are preparing Solidity style errors that we will be using later on. Here we are implementing debug for error. This is to be able to print a nice error in our terminal when we are testing it out. And next up, we have our public functions. So init here is equivalent to the constructor in Solidity. So this is what we need to do in order to actually create the this smart contract. Next up, we have we can check what token that this vault is for, the address of the token. We're getting back that address. Next up, we can query the total shares off, similar to the mapping. Here we are getting the total shares, and then we have a function that gets the shares off a specific address. Next up, we have a function to deposit tokens. So this is creating kind of an ERC contract out of the. We're fetching the address of the token, then we are using the interface for the ERC20 token to be able to send and receive this this token. Then most things here will be pretty self-explanatory. And here we have the token vault, like the non-private functions of token vault. So this is mint shares, burn shares. Shares is what you're getting back from depositing tokens. You're getting like shares, how much you are eligible for of the total supply of tokens. Yeah, that is the functions. So the task here is to implement based on what you see from the deposit tokens. You should try to implement the withdraw tokens function. So now I think that we're having a 10 minutes break. Feel free to like keep coding if you want to. And we'll get back in 10 minutes to get started with building front ends for our smart contracts. Fourth and final module of the Arbitrum workshop here. So this one is called Deploy and Go from contract to app. So now we have our contracts, both Solidity contracts as well as stylus contracts. We have hopefully deployed some contracts together. So therefore, there's one component missing to have a fully fledged app, and that is a front end. So again, if you haven't already, go to the GitHub repository that me and Alex prepared. We'll have a lot of useful links there. And for this module, again, we need testnet tokens. So make sure that you have requested testnet tokens from the Telegram channel from Alex. So we will be creating a front end using React, and we will be creating it using the VAGMI library. VAGMI is a library to interact with EVM chains. It's built on top of an Ethereum library that's called VM on TypeScript. So again, I think most of you have this already, but make sure that you have MetaMask installed, make sure that you have superposition tokens, and also that you have added superposition to your MetaMask. And lastly, we're going to go to StackBlitz. So if we change from the slides to my computer screen. Perfect. So what we're gonna wanna do first is that we want to take the GitHub repository. We want to copy this again, and then go to stackblitz.com. It will look like this. Next up, we will be open a GitHub repository here. So as you can see, we want the repository owner and name here. So make sure that you have an account already, because I don't think you can import without an account. So create an account on StackBlitz and then import it like this. Let me know when you have it imported. So you need to remove GitHub from the URL, so you only have Stylus Developers Guild / ETHCluj - 2026. Then you will press Open Repository. So it should look like this. Let me know when you're there. Also, I can explain a bit further. The main map that we want to work from is this front-end code along here. So we will be doing code along together. So what this map is, the front-end code along, is that I have used locally the pnpm package manager to install VAGMI, and then that will give me a command to create a new VAGMI project. So I did that locally as well, and this is more or less like a vanilla VAGMI project, and I have added some comments to it to make this code along a bit easier to do a bit faster. So we can also here in the terminal now change directory to this front-end code along that we want to work from. Like so. Then we can first write in the terminal pnpm install. This will install all of the dependencies that we have to run in order to. Do I need to make this a bit bigger, by the way? Yes. So let me zoom in like that. So once it's installed, we can run pnpm run dev. So this will start up a dev environment for our front end, and we can see here to the right. This is our front end right now. This is the default vanilla front end that VAGMI creates for a project. So within this front end code along, we have 3 files that is of interest for us. We have the main.tsx. This is basically where you land when you're opening this URL. This is like what's rendered. This is connected to an app tag, which is from app.tsx. This is kind of the app router. It will do all of the app-specific logic here. And this will update in real time, so I can update connection and write GM Cluj like that, and I can hit Command Save, and that will now render here on the right. Next up, we have vagmi.ts, and this is the configuration for our EVM connection. So we want to interact with superposition. So this is where we will be starting to code. So as you can see here, if we go through the code, we are importing a hook for creating a config. We're also importing pre-prepared objects for Ethereum mainnet and Ethereum Sepolia testnet. And further down here, we are creating a config with both mainnet and Sepolia. We want to swap these out to superposition. Therefore, the first step that we need to do is to import define chain from VM like this. We can save. Next up, we can uncomment this code block here. This is basically the same type of object that we imported for both mainnet and Sepolia here. So we can see that it contains chain ID, it contains the name of the chain, as well as some information about the native currency, the RPC URL, so on. So we want to use this instead of mainnet and Sepolia. So we can remove the import of mainnet and Sepolia like this, and then hit save again. And now we can see that, our app is not rendering anymore. That is because here we are trying to reach mainnet and Sepolia when we want superposition. So we can instead update this to be superposition. And then instead of having 2 lines, we're only supporting 1 network. So let's swap out here mainnet again to superposition. I can save, and now we see that it all works again. So given if I am connected to Ethereum mainnet from the start here. This is just to demonstrate something. If I press the MetaMask button here, my MetaMask will be prompted. Let's see. Okay, so I'm getting this scary-looking thing from MetaMask right now, this scary-looking alert, but this is fine because this is our own web container. Make sure that you're on Stack Blitz. So we are connecting anyway. We connect, and we see that our wallet is connected. We see here that the chain ID is 1, but we have a problem here, which is that the chain ID that we want to have is 98985. So what MetaMask is doing right now is that it's connecting to the chain ID that you just happen to be on when you're connecting your wallet. But we want to interact with superposition directly. So if you were to send the transactions right now, you would have they would probably most likely break because they would probably most likely error because it would try to send to mainnet ETH instead of superposition. So therefore, we want to write logic that on a successful successful connection, we will also update the chain. So we will write that in app.tsx. So we will go here to the hooks, and we can kind of format here a bit nicer so it's easier to read. Then we can add last here by the imports, use switch chain like this, and we can also import superposition, that superposition object that we just made from the file vagme, not the actual library vagme. Next up, we're going to go to this hook creations here. We're going to create a new hook, which is mutate switch chain equals to use switch chain, like so. So we now have our prepared hook. Then we will navigate down here because we want this to happen when we trigger this button. So we will kind of try to find here, we can find a connect header, and here is the button that actually handles our connection. So on click here, this is where we actually get connected. So we can create a new line here, like so. We can write comma here, open up new curly brackets, and on a successful connection, we want to execute a function that looks like this, switch chain, and it will send the arguments chain ID superposition.id, like so. So I hit command save again. Now I disconnect, and now when I'm connecting my wallet, it should connect to the 98985 instead of chain 1, and you can see that it did. So now we're connected to the correct chain. Next up, what I want to do is that I want to interact with the wrapped Ethereum address of superposition. So the wrapped Ethereum address is a standardized, or wrapped Ethereum contract is a standardized contract that exists on more or less every EVM chain. It takes the native currency and wraps that into an ERC20 token so that you can have your native currency interact with other smart contracts. And in the case for superposition, since the native currency of superposition is not Ether, it's superposition, then it will be called wrapped superposition on superposition. But I will use these terms kind of interchangeably, just so you know. So what I want to do is that I want to interact with this contract. So in order to interact with the contract, I need two things. One, I need the address of the contract. So for that, we can go to the testnet explorer of superposition. We can browse the tokens here, and we can find the wrapped superposition here. So we can see here, I can open this up. We can see that the address is 214C. Let's see if looks like it's a bit slow. Here 214C, and I already prepared this constant here, which have the 214C. So I have the wrapped Ethereum address here. So I will just uncomment this. Secondly, we need something that's called an ABI. So an ABI is basically this huge JSON object that is telling us how we can interact with the smart contract. It's basically like guardrails to interact with the smart contract. So it will tell us what function signatures we have available and how we can interact with these. So unfortunately, the wrapped superposition token is not verified, so I can't get it from here. Here I will just get this huge pile of opcodes here. But I can go to, since it's standardized and the same on every chain, I can go to mainnet EtherScan, and I can browse for tokens here instead, look for the top tokens, and we can see that we have wrapped Ether here. And from here, I can read the contract and get the ABI. So this is kind of how the ABI looks when I get it. Same as with the address, I have already prepared that. So if you go to inside of our front-end code along to ABIs, we have the wrapped ethereum.ts. It actually exports the entire ABI. So from app here, we can import wrapped Ethereum ABI from ABIs slash started with like that slash we like that. Then in order to, what I want to do from the start is that I want to read the total supply of wrapped Ethereum, how many wrapped superposition does it exist. We can see here on the scan that there are approximately 3.5 million wrapped superposition. So in order to do that, I will be using a read function that's called total supply. So use read contract is the hook that we want to use. Then here we can create our call, which will look like this: const data is total supply, and that is use read contract, and we need to send in some information here. So first of all, we need the ABI like this. Then we need the address like this. Lastly, we need the function name. So function name is, and it's a string, so total supply like that. Then we can go to the bottom of our page here. We can add a tag like this and write total supply is, and then we can have inline here, total supply. So let's save that again. We can see that it pops up. So we see here that we get this huge number here with one problem. We don't have any decimals here. If we go through the superposition testnet here, we see that it is 3.5 million and it is 76.5. And if we go to that decimal point, 76.5, we can see that the decimal isn't inserted. This is because the EVM can't handle decimals whatsoever. It's only full numbers, and therefore every smart contract stores the decimal point as well. So you have to export the decimal point as well as the number in order to actually be able to render this correctly. This comes down to that computers in general are horrible at handling decimals, and since the EVM is kind of like a financial thing, it's kind of important to get numbers right. So then to get the decimals, we can just copy the code from total supply here. Copy this, do it like that. It's decimals, and then we will need to format this in order to in order to render this correctly. So we will use from VM import format units. This will use these decimals in order to display it correctly from VM. But now we're about to do like math on top of these numbers that we're getting back from the blockchain. And the problem here is that whenever we're reading from the blockchain, that is actually us sending a request over the internet, an API request, to actually get that number back. There's no guarantee that we actually get what we expect back from that. We wish to get the number, but we can get something else. We can get an error. A lot of things can happen on the way. This VAGMI library solves that by either giving you what you want, or it will give you undefined. And same as with the Rust logic, when you're trying to operate over this number, if it is undefined, that will completely break. So therefore, we kind of need to take this in consideration now when we're about to format the results here. So instead of displaying total supply like this, we can open up a curly bracket here. We can create a condition, an if-else statement. So if total supply is not equal to undefined, meaning that if we actually get the format that we expect from total supply and not an undefined, and if decimals is not equal to undefined, then we will be printing total supply is then format units, total supply, and decimals. If, however, any of these two isn't, like if we fail to fetch either total supply or decimals, we will instead send back could not get total supply. So now we can save again, and now we can see that when we update that we do get 3.5 million, and we get that 76.5 correct decimalization. So very good. Lastly, I want to, because right now we're just reading from the contract. If we want to send a function that is actually interacting with this contract, like hitting a state changing function, then we can use the very intuitively named, since we just use read contract, we can use write contract. In order to use this, we can create a new function here, which will be a tag. So function mint, like that. Mint will return a couple of HTML here. So it will return form. We don't need an action just yet. We have a header in the form, which is called mint wrapped superposition, and we're excited, so we do a couple of exclamation marks. Then we will create an input field here. The input field will be of type number, and we can format this a bit nicer like this. So name is amount to mint, ID is amount to mint, and step here, which is like the decimal precision that we have for this input field, is 0.001. This will give us like 3 decimal precision when we are changing the number. Otherwise, it will just be whole numbers. We will create a label for this, which will be a label for amount to mint, which says amount, like that. Lastly, we will create a button, which will say mint. Button will be of type submit. Then down here, we will be adding the tag that we just wrote. So mint, like this. So we can save that, and we can see that we're getting this mint mint button here. Right now, it doesn't really do anything. If I press it, it just like refreshes because we haven't implemented any of the logic to do that yet. So now I set on form here, we set on submit equals to then mint. So we will create a mint function within the capital mint function. So async function mint, it will take e, which is react dot submit event, and it will take HTML form element like that. So first of all, we want to prevent the possibility that someone just hits the submit button when we don't have any text here. So therefore, the first line will be e.prevent default, like that. Next up, we want to fetch what we actually got here from the amount to mint. So we do that by first creating one const that's called form data, which is a new form data from e.target as HTML form element. Then we want to extract the amount to mint from this. So const mint amount equals to form data dot get, and we're sending in the key amount to mint in here. So now to set up our hook here, our write contract hook, we are writing const data hash, then write contract equals to use write contract, like this. Then the actual call is very similar to the use read contract. So we will use write contract, then open up like this, and we're sending an ABI, which is wrapped Ethereum ABI. We are sending in the address, which is wrapped Ethereum address, function name, which in this case is deposit. And lastly, we want to send in a value too, and this value will be the mint amount. But remember what I said, that the EVM can't handle decimals, and right now this form is using decimals. So like you see, like I will type in 0.01 or something like that. Therefore, we must be able to handle that too. So within this import for format unit, we will add another import with it, which is parse ether. This will take a regular number and parse that into an ether value correctly. And that will take a string, so therefore we must take this as string. Then we update here, so value is equal to parse ether, and into that we're sending the mint amount, like this. I think this is it. So lastly, we want for our users, we want some feedback for them to know if their transaction actually went through or not, because right now it would just be me pressing the mint button, and then I would have to, I don't know, guess if my transaction went through or not. So let's create that as well, that logic. So if we get a hash, then we will render a p tag like this that says transaction succeeded, hash is equal to then inline hash, like this. So I press save again, and now fingers crossed, we want to mint 0.001 wrapped superposition. So I hit mint, and it should trigger my MetaMask, and I need to acknowledge that I am fine with this. So here, now we can see that transaction succeeded, hash, and I get the hash. So I can copy this hash, and again, go to the SuperNet testnet explorer. I can search this hash, and the explorer is a bit slow, so right now it hasn't found the matching result. If I try to refresh, we can see that I have my transaction here. So I can go into this. I can see that I indeed minted 0.001 superposition tokens, wrapped superposition tokens, and this happened 25 seconds ago. So this is how you would write a front end using the Wagmir library in React. So the last and final challenge here will be for you to use the previous contracts that we deployed. So, for example, if you want to deploy something from our MetaMask or from the remix here, where we were implementing, not this one, but actually the one here. If you want to deploy anything from Solidity Challenges solved here, smart contracts, or if you want to deploy anything from the wizard with the vault that we were creating, and then you will take that contract address and you can create. It's kind of an open-ended challenge here. So through Stack Blitz here, create your own front end for that contract. So I will be here around to help you with any questions that you might have during this process.